Hello, this is Mr. Gilmore with the 9.2 The Inscribed Angle Theorem lesson. Today we're going to be looking at a new type of angle known as an inscribed angle and its relationship to the arc that it cuts. Let's take a look and dive into this lesson. So we begin with our definition of what this inscribed angle is. Simply, it's an angle whose sides are chords. If we take a look at the diagram below, we find our inscribed angle, angle BAC. Now, if you take a look at the diagram, we have the chords A, B, and AC. Now, both of them sharing point A, which means we do actually form this angle whose vertex lies on the circle. Thus, we have ourselves an inscribed angle. So we're going to be taking a look at the inscribed angle and the arc it cuts. Notice that if we were to go back and look at our central angles, remember, have the vertices at the center of our circle. Imagine then dragging that vertex so that it is on the circle. That still cuts an arc, and this angle BAC has a relationship to this arc that it is cutting. So we're going to dive into the relationship that these two parts hold together: the measure of the arc, the measure of the inscribed angle BAC, and the measure of the arc that it cuts. So thus we have what's called the inscribed angle theorem, or to us the IAT. Let's dive into what this says. It says that the measure of an inscribed angle is half the measure of the arc that it cuts. In other words, if we take a look at the diagram below, the measure of our inscribed angle BAC is actually equal to half the measure of the arc that it cuts, BC. So we could kind of play the numbers game here if you want to just see some examples. If I were to say that the measure of this inscribed angle here, BAC, was 45 degrees, then the measure of the arc it cut is 90 degrees, right? It's because the measure of the arc has got to be measure of the inscribed angle is half the measure of the arc it cuts. We could also play the game backward. Let's say I were to tell you that this measure of the arc is 120 degrees. That means then the measure of the inscribed angle is half of that, so we're looking at 60 degrees is the measure of the inscribed angle. And that's what we're going to prove with the inscribed angle theorem, such that this is a true result. As it turns out, though, the inscribed angle theorem actually breaks it into three cases. Let's take a look at what case one is. Case one is our special case, because with our inscribed angle, we're going to find that the two sides of our chords, or two sides of our angle, pass through the center, or pass through the circle as chords. Well, one of the special cases that could actually happen is when one of the sides of our angle is actually a diameter. That means it passes through the center of our circle. So in other words, take a look at our diagram below. We have this inscribed angle BCD, such that one of its sides, BC, is passing through the center of the circle at point A. We're going to find that this is going to be kind of the foundation of our proof and inscribed angle theorem. And what we're going to prove with this first case, having that side be a diameter, we're going to prove again that the measure of our inscribed angle BCD is equal to half the measure of our arc BD, the half the measure of the arc that it cuts. So let's dive into what this proof actually looks like. So case one proof is a bit more intensive than the other two cases. Let's take a look at what we have set up again. We have our circle A, such that we do have our inscribed angle BCD, and BC is a diameter, which means it's side of the angles passing through the center of our circle. Let's prove that the measure of our angle BCD is equal to half the measure of arc BD. Well, let's start off then with the given. Let's connect point A to D. By doing that, we actually form another radius. And with this radius, it has relationship with another radius within the side of our circle. AD and AC are actually equal by definition of radius. What we're doing then is we find that we've actually constructed ourselves strategically an isosceles triangle ADC, which means now by the ITT we can claim that the measure of our angle BCD is equal to the measure of our angle ADC, and we'll see that the relationship is going to come in handy here in just a moment. Now, the angle BAD is both an exterior angle and a central angle by definition. Take a look at the angle BAD. See that angle right there, BAD? That angle BAD, actually there's two things going on. Because it is exterior and that it's a central angle, we actually have these two relationships that we're going to build with that central angle to our inscribed angle BCD. So let's take a look at what the equation unfolds as we use the triangle exterior angle equality. This is something way back in chapter 4. Because this exterior, we can say that the measure of its two remote angles, I should say the sum of the measures of the two remote angles, is equal to the measure of the exterior. So in other words, we have the measure of angle BCD plus the measure of angle ADC is equal to the entire central angle measure there, BAD. And by our arc measure postulate, the measure of that central angle, BAD, is equal to the measure of the arc it cuts, which is simply just the measure of arc BD. And it just so happens the measure of arc BD is that same arc that our inscribed angle is also cutting BCD. So with substitution, with our equation we saw with our triangle exterior angle equality equation, we can replace ADC with BCD, and we can replace the measure of our angle BAD with the measure of our arc BD. So what we have then is the measure of angle BCD plus the measure of angle BCD is equal to the measure of our arc BD, or rather, 2 times the measure of our angle BCD is equal to the measure of arc BD. And finally, with the division, we get the measure of our angle BCD is equal to half the measure of the arc it cuts, BD. There we have it, QED, the proof of case 1. Let's move on to the other 2 cases. Let's take a look at case 2. So if one of our cases, such that, or case 1, was that the one of the sides passes through the center of our circle, well then the other 2 cases, case 2 and case 3, actually revolve around where else could that center of the circle be. In this second case, we find the center of our circle could also then be on the interior of the 2 sides of our angle. So imagine, right, we have BC is this angle cutting through, BD is this angle cut through, and it turns out point A is on the interior of those 2 angles. We have the 2 sides of our angle of our inscribed angle BCD. Well, we're going to prove then with the measure of measure of our inscribed angle there BCD that it's actually going to be half the measure of the arc it cuts, the measure of arc BD. Let's dive into the proof of case 2. So the proof of case 2, not as bad, and here's why. We can actually tap into the first proof, the inscribed angle theorem case 1, because that's a distinct case. We can actually use that in our case here for case 2. So again, we have our circle A with the inscribed angle BCD, where center A is on the interior of our angle BCD. Let's prove the measure of angle BCD is again half the measure of the arc it cuts. What we're going to do first, once we've got our given all set up, we're going to use our given. We're going to construct a diameter through point C and A, right? So that is a diameter passing through a center. And we'll call that opposite point there that's intersecting the circle point Z. So now, take a look what happens. We now have produced 2 angles, BCZ and DCZ, such that those 2 angles are inscribed angles that have a side as a diameter. And because of that, we can use inscribed angle case 1. So the inscribed angle theorem case 1 says that the measure of our central angle BCZ is going to be equal to half the measure of the arc it cuts, which happens to be our arc BZ. And the measure of our inscribed angle DCZ is going to be half the measure of the arc it cuts, which is this arc DZ. Well, notice that the sum then of these equals and equals, they're going to add up to the whole pieces of information. Well, they're going to add up to the entire inscribed angle BCD and the entire of the arc that it cuts BD. So we take our equals, we add them to equals, and then last by our angle addition postulate and our arc addition theorem, we have ourselves the statement we were looking for, that the measure of our measure of our inscribed angle BCD is equal to half the measure of the arc that it cuts, the measure of arc BD. Now on to our case 3. In case 3, we now have our last option for our center, and that is where the center passes on the outside or the exterior of the mouth of our inscribed angle. So notice again, BCD cutting through our circle, and the ray CB and ray CD. Point A is not a point on the interior of the mouth of that angle. We're again going to prove the measure of the inscribed angle BCD is half the measure of the arc it cuts. Let's take a look at case 3. Case 3, not much different from case 2, because we are going to find ourselves with a construction that gives us inscribed angle theorem case 1. So once we've got our given and our proof statement and our diagram all set up, we dive into the proof, which says with the given, construct diameter CZ again. So we construct diameter CZ such that, again, diameters pass through the center A, and that means we actually have 2 angles here that have a side, which is a diameter. Now, we have to be careful here. The first angle is pretty obvious. It's DCZ. Look at that angle there, right? It has a side as a diameter. But the second one is actually this entire angle, BCZ. Well, we want the part that's here, right? We want that part, which is only part of the whole angle BCZ. However, What we also know is that if we have equals and we take away equals, we will be left with equals. So you're going to see that come up in our proof in just a moment. So now that we've got two angles there, BCZ and DCZ, which are actually the same two angles we saw in case 2, we can claim that they are actually equal to half the measure of the arc they cut. So the entire angle BCZ actually cuts the entire, or cutting this entire arc BZ, which is then half of BZ, and the inscribed angle DCZ is cutting this arc here, DZ, which means the measure of that, half the measure of that arc is equal to our inscribed angle there. So we've got the measure of angle BCZ is equal to the half the measure of arc BZ, and the measure of our angle DCZ is equal to half the measure of arc DZ. By the subtraction property this time, not the addition property, but subtraction property, we can take equals away from equals. And then last, again, by using the angle addition postulate and the arc addition theorem, we arrive to our conclusion, because what we're doing is really the whole minus part. Taking the whole angle and subtracting off a part of our angle, we get the remaining part. And we take the whole arc, subtract off part of the arc, and we're left with the remaining arc. Thus, we arrive to our conclusion a third time: the measure of the inscribed angle BCD is equal to half the measure of the arc it cuts. Now that we've seen all three cases in action, what each of these do is they build the complete picture and nature of our inscribed angle theorem. So when working with inscribed angles now, you do not have to refer to them specifically by case. You can just say, hey, each of three cases covers the entire theorem, the IAT, which means when I encounter an inscribed angle, I could just simply say it's half the measure of the arc it cuts, and then just mention the inscribed angle theorem as a whole, because these three pieces cover all different cases with our chords in the circle. Now let's just do a little bit of reflection as we end our lesson today. So note that the three proofs really were distinct. We could not just prove case 1 and just say rinse and repeat for the others. No, we needed actually three distinct proofs for case 1, case 2, and case 3. But you'll also notice case 2 and case 3 were really just corollaries of case 1. They were just these instant consequences of having this other significant part of our inscribed angle theorem. So case 2 and case 3 really are corollaries of case 1. However, they also are distinct. Case 2 was we use the case 1 twice, but then add. And case 3 was we again use case 1 twice, but then we subtract. And that's what makes all three of these cases distinct from one another. Be sure then, we're at the end of our lesson, be sure to hop over and take a look at the worksheet 9.2 and be working with the inscribed angle theorem. If you do have any questions on that worksheet, please do not hesitate to email me. With that, be good and do good.